Welcome to this third lecture of the course Applied Stochastic Differential Equations. The topic of this lecture is probability distributions and statistics of SDEs. We will start by introducing the Fokker-Planck-Kolmogorov equation, which is a partial differential equation for the distribution of an SDE. Then we will show how to compute the mean and covariance and higher moments of SDEs. Then we will specialize those results to linear SDEs. Then we discuss the Markov properties of SDEs as well as the transition densities of linear and nonlinear SDEs. Then we will summarize the lecture. Let's now start with the Fokker-Planck-Kolmogorov equation. Start by considering the following stochastic differential equation, which is dx is equal to f of x and t dt plus L of x and t times d beta, where beta is a vector of Brownian motions. Now each x with fixed t is a random variable, which has certain probability distribution. So this probability density of this distribution is denoted with p of x and t. Or sometimes we write p of x as function of t. The probability density is a solution to certain partial differential equation, which is called the Fokker-Planck-Kolmogorov equation. The distribution also has certain mean and covariance, which are functions of t, and they are solutions to certain ordinary differential equations. However, it turns out that solving these equations is not so straightforward, but anyway, in principle, we can write them down. And in the linear case, they turn out to be very useful for the actual computation of the mean and covariance. Let's now derive the Fokker-Planck-Kolmogorov equation, which is the partial differential equation for the state of an SDE. Let phi of x be an arbitrary twice differentiable function. Then, if we use the Ito formula, we can write down the Ito differential of phi as follows. d phi is equal to the summation of partial derivatives of phi with respect to each of the x variables times the corresponding fi's dt plus the summation over the same partial derivatives times the corresponding dimensions of L times d beta plus then half times the second derivatives of phi with respect to each of the pairs of x's times then the elements of matrix LQ, L transpose, then times dt. Now taking expectations of both sides, we get that the term with d beta disappears because the expectation of d beta is 0, and then we can proceed to divide formally by dt, which gives this differential equation for the expectation of phi. Let's now take a look at the first term on the left. So the term can be written like this. So the time derivative of the expectation of phi is equal to the time derivative of integral of phi of x times the probability density of x at time t dx, and assuming that we can exchange the order of differentiation and integration is equal to the integral of phi of x times the partial derivative of p of x and t dx. Now let's recall the multidimensional integration by parts formula. So the integral over area C of the partial derivative of u with respect to xi times v of x dx is equal to the boundary integral of u of x times v of x and the normal and the surface element minus the integral over c of u of x, the partial derivative of v with respect to xi dx. And in our case, because c is infinite, the boundary term vanishes, and we actually have this kind of integration by parts formula. So the integral of the partial derivative of u with respect to xi v of x dx is equal to minus the integral of u of x times the partial derivative of v with respect to xi dx. So we just exchange the differentiation from u to v and put minus in front. Let's now return to our equation, which currently looks like this. So the time derivative of phi which is equal to the integral of phi of x times the partial derivative of p dx is equal to the Ito formula result, which is the summation of expectations of partial derivatives of phi with respect to xi times the corresponding fi's plus half times the expectation of second derivatives times the elements of LQ, L transpose. For the first term on the right, we will now use the integration by parts. So the expectation of the partial derivative of phi with respect to xi, fi is by definition equal to the integral of the partial derivative of phi with respect to xi times fi times the property density of x dx. As we saw in the previous slide, the integration by parts formula in this case just changes the differentiation from the left-hand term to the right-hand term, and then we add another minus in front. So in our case, we take the differentiation away from phi and move it to the term fi times p, which gives this result. So now we only have one term to go. For the remaining term, we will use integration by parts formula twice. So the expectation of the second derivatives of phi times the elements of LQ, L transpose is equal to the integral of the second partial derivative of phi with respect to xi exchange times the corresponding element of LQ, L transpose times the property density of x dx. And now we can use the integration by parts formula for the partial derivative with respect to xi. So we will take it away from phi and move it to the term LQ, L transpose times p. And then we add a minus. So we will get this kind of expression over here. And then for the partial derivative with respect to xj, we will do the same. So the minus will disappear and we will have this kind of expression. After all these manipulations, our equation now looks like this. So the integral of phi of x times the time partial derivative of p dx is equal to minus the summation over phi of x times the partial derivative of fi p with respect to xi dx plus half times the summation of integral of phi of x times the second partial derivatives of the term LQ, L transpose p dx. And now we can combine all the integrals and take phi out, which allows us to rewrite this equation like this. So the integral of phi of x times a term in the brackets, which is the partial derivative of p respected to t, plus partial derivatives of fi p minus half times the second partial derivatives of LQ, L transpose p, and the integral over x should be 0. But now the function phi of x was arbitrary, and it turns out that this integral can only be 0 for arbitrary phi if the term in the brackets is 0. And this term in the brackets gives us the Fokker-Planck-Kolmogorov equation. Our result now looks like this. So the probability density p of x and t of the solution to the SDE, which is given as dx is equal to f of x and t dt plus L of x and t d beta, is the solution to the Fokker-Planck-Kolmogorov equation, which is a partial differential equation of this form. So it says that the time partial derivative of p should be equal to minus the summation over the partial derivatives of fi p with respect to xi's plus half times the second partial derivatives of the term LQ, L transpose times p. In physics literature, this partial differential equation is called the Fokker-Planck equation. However, in stochastics, it's usually called the forward-Kolmogorov equation. So for these reasons, we have chosen to call it Fokker-Planck-Kolmogorov equation. Let's now take a look at an example application of the Fokker-Planck-Kolmogorov equation. Assume that our SDE is actually given by dx is equal to d beta. Of course, this is just another way of saying that x is equal to beta, but in this form it's easier to see that it's actually a special case of an SDE. Let's assume that the diffusion constant of the Brownian motion is equal to 2d. So what we get is that the time partial derivative of p is equal to 0 for the first term plus half times 2d over 2, so 2 disappears, times the second partial derivative of p with respect to x. So it gives the diffusion equation, which we already derived from the Einstein's results during the first lecture. As another example of the use of the Fokker-Planck-Kolmogorov equation, let's now take a look at the Benesch SDE, which looks like this. So the SDE is given as dx is equal to hyperbolic tangent of x dt plus d beta, where beta is assumed to be a standard Brownian motion. Now the Fokker-Planck-Kolmogorov equation is the time partial derivative of p is equal to minus the x derivative of the term hyperbolic tangent of x times p of x and t, plus then half times the second partial derivative of p with respect to x. But now if we expand the first term, this is equal to hyperbolic tangent squared of x minus 1, then times the p of x and t, minus the hyperbolic tangent of x times the partial derivative of p with respect to x, plus then half times the second partial derivatives of p.